It began with one team, one goal, and the discovery of new solutions. When we began working with our first racing team, we took on the challenge to improve the performance of the valve train. Our engineers began an in-depth study to identify the right coatings and precise application processes that were best suited for the extreme conditions of performance racing. We met regularly with the team to conduct tests on components to see how well their new coatings and technologies stood up to abrasion, fatigue, and heat. What began as an experiment has grown into racing plasma, an industry standard. NCT's Racing Plasma is now the preferred plasma-enhanced surface treatment designed specifically for the performance racing industry, used by elite racing teams around the world. Racing Plasma assures the performance and reliability of your components, enabling you to perform beyond standards, race after race. The purpose of surface treatments is to overcome the common enemies of prolonged performance: heat, friction, and fatigue. In an average race, a high-performance engine can lose 20 horsepower or more. Racing Plasma surface treatments preserve more of the original build power of the engine and maintain the component's efficiency under the most grueling demands. There are many approaches to optimize an engine's performance, and your unique requirements may not respond to a typical solution. We work with you to find the optimum surface treatment that will provide the greatest performance. We focus on two types of plasma-enhanced surface treatments: PVD, or physical vapor deposition, and plasma ion nitriding. The PVD process, shown on the left, adds a protective layer of metal to your component. A metal film is added ion by ion to the specific areas that need protection. We'll be taking a look at how this treatment benefits valves. The plasma ion nitriding treatment, shown on the right, changes the molecular structure of the surface of the component. Also known as case hardening, this process affects the outer shell of the existing material, improving the fatigue life of the component. Valve springs, retainers, spring seats, and crankshafts are examples of parts that benefit from this process. Let's take a closer look at the process. When we begin, we place the parts to be treated in a specially designed rack in preparation for a solvent bath to remove surface contaminants. The basket ensures the proper drainage and protects the valves from any damage. An automated cleaning process ensures consistency. The components are lowered into the ultrasonic cleaning tank, which will remove additional contamination that might be on the surface. The first part of the cycle is done. The parts are raised slowly out of the first bath to be sure they've fully drained, and then they are introduced to the vapor side, which is a boiling, ultra-clean solution. This way, any possible remaining surface contaminants are rinsed away. After the entire cleaning cycle is complete, this basket is then taken to an inspection area. Each component is inspected by a technician who places them in the treatment rack. Masks are placed on the areas of the components which will be excluded from the treatment process. Only the exposed surfaces will be treated. Now, onto the treatment chambers. Physical vapor deposition, commonly referred to as PVD, is a process in which a coating is added to a component ion by ion. The PVD process creates a uniform layer with a thickness so precise and consistent that engineers can anticipate the increase of the dimensions when they design the components. During the PVD coating process, the parts are placed into the chamber on a carousel. The atmosphere is removed and the parts are brought to a preset temperature. The cathode ignites and begins to evaporate the source material. A reactive gas is introduced into the chamber as the source material is being evaporated. This reactive gas can be a mix of gases or a single gas. As the source material is evaporated, it is ionized. The free-floating ions are drawn to the parts via a negative bias applied. The ions reacted the surface of the parts with the reactive gas to create a new metal compound which adheres to the part on a molecular level. A PVD coating minimizes fretting and abrasive wear, reduces friction, protects against material transfer, and provides a barrier against elevated temperatures. For example, the part of the valve that takes the worst beating is the seat. When this part is treated with the racing plasma PVD process, the seat looks the same at the end of the race as it did at the beginning. As a result, compression is retained throughout the course of a race. We know racing teams are always searching for the highest level of performance, so our staff continually works to develop new metallic film coatings. Your unique requirements will determine which coating is recommended. Titanium nitride, titanium carbonitride, aluminum titanium nitride, chromium nitride, zirconium nitride. Plasma nitriding, the blue glow process, also known as case hardening, is a thermochemical diffusion process that creates a case-hardened layer by changing the chemical structure of the surface of a component. Recommended applications include valve springs, retainers, spring seats, and crankshafts. Nitriding is used on components with a ferrous base and can be very carefully controlled to impart a precise case depth. This allows the component to resist abrasion and reduce the material's tendency to gall when in use. This process will extend the fatigue life of the component being treated and is used when the product experiences extreme loading or torque, or when the core hardness does not lend itself to supporting a PVD coating. With plasma ion nitriding, components are placed into the chamber and the atmosphere is removed. The chamber is then backfilled with a hydrogen gas and the components are heated to between 900 and 950 degrees Fahrenheit. A plasma is generated by an electrical charge that is applied to the components. A gas mixture containing nitrogen is introduced and the nitriding cycle begins. The nitrogen present reacts with the iron in the steel to form a compound layer of iron nitride on the component's surface. This surface layer is the supply for the nitrogen to diffuse into and react with the nitride-forming elements in the component, which include chromium, titanium, aluminum, or vanadium. A constant supply of the gas mixture is fed into the chamber to sustain the nitriding process and produce a uniform case depth. When the designated processing time has elapsed, the plasma is extinguished and the product is allowed to cool. Our gamma prime layer is used when a small white layer buildup is required and where impact may be a concern. Our epsilon layer is used on low alloy steels, cast irons, and when a thick white layer is necessary. Our duplex layer is used when we will be applying one of our PVD coatings to the surface of a material that will not provide sufficient support. The hard case developed from the nitriding process provides a hard surface which bonds more easily with the PVD coating. Back to the PVD-treated valves. After the treatment process is finished, the batch is brought into the inspection and packing department where each component is thoroughly inspected again. The inspector uses a magnifying glass to scrutinize each piece. In every single batch of processed parts there is a witness sample, which receives the same treatment as the components. This sample is retained with all batch records so that there is a physical identifier here at NCT for every single run. Periodically, we take one of the finished components to examine the actual treatment layer. Our technician chooses a sample. The part is sliced to expose a cross-section of the treated metal. It is then placed in an examination medium which is polished. The cross-section specimen is then reviewed using our image analysis system. The technician examines the sample to determine if there are any irregularities. This PVD coating is uniform and consistent and has the proper thickness. The process is so precise that we can consistently produce a layer that is 1/10,000th of an inch thick, repeatedly. NCT's racing plasma treatments have become the standard for the performance racing industry because of our ability to guarantee a superior result. Uniform protective coatings and a process which can be exactly and infinitely replicated. Racing plasma assures the performance and reliability of your components, enabling you to perform beyond standards.